So in the last lecture, we were looking at how NMR signal relaxes, and using block equations, actually we saw how the complex NMR signal looks like. So what we had was the NMR signal can be thought of as a linear combination of real and as a complex signal, basically, where it is composed of real signal and imaginary signal, and where the real part is given by cos of capital omega t e to the power minus t r2, and imaginary part was given by sine of offset t e to the power minus t r2, and this looks something like a decaying cosine wave. And this signal looks like something like a decaying sine wave. And so on, right? Okay. So, and here basically you can extract the offset and R2 out of this, and similarly extract offset and R2 out of it, which is the information required for a given nuclei when we are recording the NMR spectrum. Now, but life is not so simple, so you barely have a single proton. So this was the case when you have a single proton. Now let us say that you have uh, a sample which has three different protons, and as I explained earlier, that each of this different type of protons will have its own offset, right? So you have methyls resonating at their own offset, so their Larmor precession will be different, and that's how their offsets will be different, right? So offset of CH2 will be different and offset of OH will be different. So that means instead of a single cosine wave, you will have a linear combination of three cosine waves with three different frequencies. So what I mean is something like that. So your signal looks something like this is, let's say, the first frequency, then so you have, let's say, the other frequency going like this, and then you have a third frequency, let's say, which is going like this. All of these are simultaneously detected, right? Now similar thing will happen in the imaginary signal also, but I'm not drawing that. Okay, so now so instead of looking like a simple cosine wave, this actually looks becomes a linear combination of three cosine waves, and it looks like something this. Basically you can't really predict the oscillating part and the rate part of three different frequencies. All of these can have three different R2 values also. So R2 CH3, R2 CH2. It may or may not be different, but uh, the offsets will definitely be different for each. Okay, yeah, offsets can also have accidental overlap, so it can also be similar. But the idea is, if you have three different protons, it can have three different frequencies and three different R2 values, giving you a crappy looking FID, right? So now how do you extract out the different frequencies and different R2 rates from here, right? So what we do is we use something called as Fourier transformation here. So what we have said is that this is a linear combination of all three waves. So that means if this is a linear combination, this linear combination can be deconvoluted to extract out information for each unique wave, right? So the idea of Fourier transformation is that it's a basically a mathematical technique which is used to determine the frequency and amplitude of oscillating signals contained in the time varying function. So if this is a time varying function, this is time over here. So in any time varying function, you can determine frequency and amplitude of the component oscillating signals using Fourier transformation. So let me just write down the definition, or it is a mathematical tool which was actually identified or developed much earlier than NMR was developed. So mathematical tool to determine the frequency and amplitude, which is our goal, right? We want to know how is the frequency and amplitude of individual protons or individual nuclei. Frequency and amplitude of oscillating signals contained within the time varying signal. Okay, so this is what is done. So let us see more details. So before we actually go for Fourier transformation, let us see what is a Fourier series that you must have learned in basic mathematics earlier. So let us see what is Fourier series. So when I say Fourier series, I mean that any periodic function, let us say ft is any periodic function in time, so any periodic function can be thought of or can be written as or expressed as a linear combination of sines and cosines. So what I can write as n equal to 0 to infinity, and I have an, which is the amplitude of cosine nt, and bn, which is the amplitude of sine nt. So any time periodic function can be expressed as a linear combination of sines and cosines, like this, right? So these basically it n can vary from 0 to infinity. That means n can have, or this can have any frequency, right? And similarly this can have any frequency with any amplitude. So what I mean is that, let's say if you have a square wave, I can always write the square wave as a linear combination of sines and cosines, like this, right? Something like this. So ft here is a square wave, and what I have done is I have decomposed the square wave into a linear combination of sines and cosines with different amplitudes. And now more the number of these sines and cosines, the better this fitting will be, right? That is very easy to understand. Now these sines and cosines are called as basis functions. So sines and cosines are called as basis functions and are orthogonal to each other. We'll write the orthogonality conditions here. So basically this is very similar to, let's say, if you have any random vector in three-dimensional coordinate system. So let's say you have a vector r. Now this vector r can be always, any random vector r can be always decomposed into its components along x, y and z axis, right? So I can always say that r is equal to xi plus yj plus zk, where x, y and z are components along x, y and z axis. I, j, k and are the basis functions or the unit vectors along x, y and z axis, right? So, and then I, j, k and k are orthogonal to each other. So these are the basis functions which are orthogonal to each other. Similarly, cosines and sines used here are also orthogonal. So let us see what is the orthogonality condition. So it'll be we can write it as minus pi to plus pi sine of mt and sine of nt is equal to pi Kronecker delta mn. So if m is equal to n, it will be 1. So this whole thing, the whole integral will be equal to pi. If m is not equal to n, that is two different frequencies are used, then delta will be 0. So this whole thing will be 0, right? So any two different frequencies, the signs will be orthogonal to each other. Similarly, you can write for cosine as well. So let me just write minus pi to pi cos mt, no, not sine, this is cos nt is equal to pi delta mn. And if we want to write for sine, one sine factor and another cosine factor, so this will be minus pi to plus pi sine mt cosine nt will always be 0. Okay, so if you take any two sine or cosine terms, these will always be orthogonal to each other, so this will be 0, right? So the idea is that why are we discussing this, that any periodic function in time can be thought of linear combination of sines and cosines. So that means we can always deconvolute this periodic function into its component sine and cosines, right? So this deconvolution is done by Fourier transformation. So let us now see what is Fourier transformation, and then we will go back to NMR signal. So what is Fourier transformation? So this is a as I said, it's a mathematical technique. So Fw is equal to minus infinity to plus infinity f of t, which is the periodic function, in time e to the power minus I omega t dt. This omega is a variable, and this integral is with respect to time. So basically what you are doing here is, by doing the Fourier transformations, you are converting the time domain signal into frequency domain signal. That is, you are trying to identify the frequency of each and every wave which is present in the signal, and also the amplitude. So Fw gives you the amplitude as well as the frequency, right? So this expression is called as Fourier transformation. So now if you have any mathematical function, you are able to express, you're able to calculate the Fourier transformation. So let's say if your ft is pure cosine signal, cos of offset t, this, let's say this is your NMR signal, there is no decay, there is no sine component, just the cosine part, then f of omega will be given by minus infinity to plus infinity cos of offset t e to the power minus I omega t dt. Now this, upon solving, gives you delta omega minus offset plus delta omega plus offset. Okay, so that means it gives you two signals, two delta Dirac delta functions. That means the signal will have a value, infinity value at omega equal to offset and omega equal to minus offset. Otherwise the signal will be 0. So that means you will have, let's say this is your 0, this is your offset plus, this is your offset minus. So you will get two signals like this. Okay. Similarly, if you do it for sine, so if your ft is composed of sine omega t, then fw, you apply the same formula, and what you get here, instead of plus you get a negative, so you get delta function omega minus offset minus delta function omega plus offset. That means now you have one signal going up and another signal going down. This is at minus offset. Okay, so we'll see later how we use this to actually discard one of the signal, and this process is called as frequency discrimination. When we discuss NMR's instrumentation, at that time we will see this procedure of cancelling one of the signal, which is also called as quadrature detection. So if you want, you can read now, but we'll discuss later when it comes to discuss instrumentation part. So this process is called as quadrature detection or frequency discrimination. So let's not go into that right now. So let us just see. So now that we have learned that this is how frequency domain signal is obtained from time domain signal. So your cosine wave gives you a signal which is looking like a peak now, right? So also, let's say if you have a f of t as exponential, let's say minus t r2, then you will get something like the f of omega will give you a Lorentzian function, something like this, which will have a certain line width. Okay. So this line width is equal to r2 pi. Okay, this is in hertz. Okay, so these are the examples of different if you have different time domain functions, what will be the Fourier transformation of that. So this is a purely a mathematical tool. This has nothing to do with NMR. You can have any different function and try to calculate what will be the Fourier transformation of that, any periodic function, and take the Fourier transformation of that, right? So now let us go back to the NMR signal. Okay, so as we were discussing that NMR signal is it's a complex signal, so you have real and imaginary part, and this can be also written as cos of offset t plus I sine of offset t, which comes from the mx and my part, if you remember the block equation discussion, and then you also have the relaxation part multiplied with this, right? So now Fourier transformation of this whole thing gives you s omega. So now what you are doing is you are multiplying st with the above expression I omega t, and then integrating minus infinity to plus infinity with respect to time, and then what you will get is s omega. Now this s omega will also composed of real part as a function of omega and imaginary part as a function of omega, right? Now if your real part is pure cosine wave, then your then your real part of, then the Fourier transformation of the real part will be a pure absorption spectrum and something like this. And if your imaginary part is pure sine wave, then your imaginary part in Fourier transformation will give you pure dispersive spectrum. So what do I mean by that? Let me just draw it. So what I mean is that real part will give you absorptive signal, and imaginary part will give you dispersive signal, written as a omega and d omega. Okay, so now let's go to second page. Now this a omega function looks like this: r2 divided by r2 square plus omega minus offset square. This omega is the variable, and you know the offset, you know the r2. So basically, if you see that the function maximizes at, so a omega is maximum at omega equal to offset, and it runs it decays very sharply as a function of 1 by omega minus omega square. So let me just write down: a omega decays sharply. When I say sharply, I mean by 1 over omega minus omega square as we go away from offset. Okay, so that means, like, if I try to draw it, it looks like something like this. This is my offset. So at offset the function is maxima, and as I'm moving away from offset, so as I'm moving this side or this side, the function decreases sharply, or the height or the amplitude of this line decreases sharply with this function. So 1 over omega minus omega square, omega minus capital omega square, right? So this is the Lorentzian peak, Lorentzian function. And it has a line width at half height as pi r2. Okay, this is in hertz, as I said earlier. Okay, now what happens to the dispersive part? So the dispersive signal has the form r2 over, no, not r2, sorry, this will be omega minus offset minus omega r2 square plus minus offset square. Okay, so now if you see that the function is actually 0 at omega equal to offset, so dw is equal to 0 at omega equal to offset, and it decays as you move away from offset. The decay part is by 1 is proportional to 1 by omega and not 1 by omega square as in case of absorptive signal, right? So basically the functional form is something like this. This is a lot of exaggeration, but I just want to highlight a point that so this point is omega equal to offset, and it decays less sharply as compared to the Lorentzian function. So this is a dispersive signal, and the above one was absorptive signal. So in general, we are not interested in dispersive signal because it has much larger line widths, and because of these larger line widths and the signal going 0 at the offset, the analysis becomes very difficult. So analysis of the spectra becomes very difficult. So there are overlap issues and all. So and the integration issues come into picture. So integration as in the area under the curve if you want to calculate, all those things become difficult when you have large number of protons, and if you have a larger line width, that means you have signal overlap issues, right? So dispersive signal is in general not analyzed and is discarded. So what we are interested in is the absorptive signal, which is of this shape, right, and is of a favorable line width. So now if you have, let's say if you have linear if you have the sample as CH3 CH2 OH, in which you had 3 linear combination of 3 offsets. So Fourier transformation of each of this will give you a Lorentzian peak at respective omega. And the complete spectrum will be looking like this. It will be an intensity plot against omega. Sorry for the bad drawing. So your y-axis is the intensity and x-axis is omega, okay, or the offset. It's also called as chemical shift, we will see later. Okay, so what we have learned is, using block equations, we have seen how magnetization moves and moves back, relaxes back after RF pulses is switched off, and the form of the magnetization or the motion of the magnetization is explained by block equations. Fourier transformation of that signal is then gives you the information about the offset and the intensity, and of course the line width here gives you the information about the R2 of each proton, right? So this is the familiar looking NMR spectrum, which you must be aware of. Like if you have seen NMR spectrum before, this is the familiar looking NMR spectrum. Okay, So that is all for today. So thank you very much.